Hey everyone, welcome back to Tech Adventure. Today, we're continuing our journey into the world of embedded systems and software development. In this episode, we're diving into the crucial third step of the software development lifecycle, the implementation phase or code development phase. Let's explore how this stage brings ideas to life and turns designs into functional code. In this phase, developers take the design blueprint and start building the actual code. It's one of the most exciting parts of the SDLC because this is where the software really begins to take shape. By the end of this video, you'll understand the key activities involved in implementation, including coding best practices, coding languages, code reviews, unit testing, and more. If you missed our previous video, I strongly encourage you to check it out first. It's an essential part of our learning journey and will ensure you're fully up to speed and on the same page with the rest of the content. In our previous video, we explored the second step of the software development lifecycle, SDLC, the design phase and UML diagrams in detail. Let's dive in the details of implementation phase. Let's see key activities in the implementation phase. 1. Coding. While coding, it's important to focus on programming languages. During this step, developers write code in the languages chosen during the design phase, whether it be C, Python, Java, C++, etc. During code development, teams break down the software project into smaller modules and begin coding each component. Also adhere to coding standards and guidelines. Developers follow coding standards, specific conventions, indentation, naming, and commenting to ensure readability and maintainability. 2. Code review and version control. Peer review. Code written by one developer is reviewed by others to catch potential bugs, security vulnerabilities, or performance issues. Continuous integration, CI. As code passes through reviews, it's merged into the main codebase, and CI tools check for integration issues. And for the version control, source code management. Tools like Git, GitHub, or Bitbucket track changes to the codebase, allowing developers to revert, branch, and manage code versions. Developers create branches for separate features, enabling multiple team members to work simultaneously without overriding each other's code. 3. Unit testing. Once code is reviewed and ready, it's very important to perform unit testing. Few organizations follow test-driven development, TDD, approach. TDD encourages writing tests before the actual code. As each component or function is coded, it's tested with predefined unit tests to ensure it behaves as expected. Automated testing. Automated tools help to validate smaller portions of the code, ensuring that each module functions correctly in isolation. Bug fixes and refactoring. If issues arise in unit tests, developers refactor the code immediately and test again to maintain quality. Testing part we will see in more details in our upcoming videos. 4. Documentation. Code documentation. Developers document functions, classes, and modules so other team members and future maintainers can understand the code base. User manuals and technical guides. Alongside code comments, technical writers may document instructions for end users or administrators, detailing how the software should be used or configured. Now let's see the best practices in the implementation phase. Best practice for the implementation phase. 1. Adopt coding standards. Standardize the code style, naming conventions, and formatting to improve readability and consistency across the team. 2. Use modular and scalable code. Write code in modular, reusable components to minimize redundancy, making it easier to troubleshoot, upgrade, and maintain. 3. Frequent testing. Regularly run unit and automated tests to detect bugs early, ensuring the code functions as expected. 4. Encourage code reviews. Conduct regular peer reviews to catch issues early, improve code quality, and promote knowledge sharing within the team. 5. Use version control effectively. Manage branches with proper naming conventions and merge policies to prevent conflicts and track changes easily. 6. Adopt CI and CD pipelines. Use continuous integration and continuous delivery tools to automate testing and deployment, reducing errors and keeping code in a deployable state at all times. Here are major tools used in implementation phase from the perspective of embedded development. 1. Integrated Development Environments, IDEs. Embedded specific IDEs. Tools like Keil UVision, IR Embedded Workbench, VS Code, and Eclipse IDE for C or C++, CDT, are popular in embedded systems development. These IDEs provide features like syntax highlighting, debugging, cross-compilation, and integration with hardware debuggers. 2. Version control systems and continuous integration. Git, GitHub, and GitLab are widely used in embedded development to track code changes, manage branches, and collaborate across teams. These systems help manage firmware changes and updates for embedded devices. Continuous integration, CI, tools. Jenkins and GitLab CI are commonly used CI tools in embedded development to automate testing and building firmware for embedded devices. They can trigger builds when code changes are pushed and run automated tests on emulators or real hardware using hardware-in-the-loop, HIL, testing setups. 3. Testing frameworks. CPPU Test, Tessie, VectorCast, Google Test, and Unity Test Framework. These are widely used for unit testing in embedded systems, helping developers test individual components of firmware. Embedded emulators and simulators. These are also essential for testing code before deploying on actual hardware. 4. Documentation tools. Doxygen is extensively used in embedded development for generating code documentation. It supports C and C++, which are popular in embedded programming. Confluence and Notion are used for collaborative documentation, storing hardware configurations, design specifications, and team knowledge in embedded projects. 5. Static code analysis tools. PCLint, CPPCheck, and Coverity. These are popular static analysis tools for embedded C or C++ code. They automatically check for coding standard violations, such as Mishra C, which is often used in safety-critical embedded software, syntax errors, and vulnerabilities, ensuring compliance with industry standards. And many more tools are used across various industries, tailored for different types of software, applications, and product-based development. These tools are chosen based on the specific needs of the project, the type of software being developed, and industry requirements. Roles involved in the implementation phase. 1. Software developers. Write and implement the code, perform unit testing, and integrate the code into the overall system. 2. Test engineers and quality assurance. QA conduct unit tests, validate that modules function correctly, and raise any issues found. 3. Technical leads or architects. Oversee the code structure, ensure adherence to design principles, and review code for compliance with quality standards. 4. DevOps engineers. Manage CI and CD pipelines, ensure smooth integration and deployment, and maintain the infrastructure required for development. 5. Technical writers. Develop documentation for code, configuration, usage, and maintenance. 6. Project managers or Scrum Masters. Facilitate progress by ensuring developers meet deadlines, remove obstacles, and maintain focus on project goals. Challenges in the implementation phase and how to avoid them. 1. Managing complexity. Large projects with multiple interdependent modules are harder to manage because integrating and testing the code requires coordination across various components. Breaking down the system into smaller, manageable components and adopting modular development can reduce complexity. Properly defined interfaces between modules and thorough documentation can also make integration smoother. 2. Quality versus deadline. Developers often face pressure to meet tight deadlines, which can result in trade-offs between writing high-quality code and rushing to deliver on time. Prioritizing key features, using agile methodologies, example, iterative development, and focusing on continuous improvement can help maintain a balance between speed and quality. Early testing and frequent code reviews also help prevent long-term technical debt. 3. Team coordination. When multiple developers work on different modules simultaneously, code conflicts and integration issues can arise, requiring careful coordination. Using version control systems, example, Git, clear branching strategies, and regular communication between teams can minimize conflicts. Daily stand-ups, continuous integration, CI, and automated tests can help detect and resolve issues early. 4. Debugging and testing. Debugging and testing in complex systems is often time-consuming and requires a systematic approach to identify and resolve errors. Automated testing tools, including unit tests and regression tests, can help catch bugs early. Additionally, using debugging tools that integrate with IDEs and emulators for testing in controlled environments can help identify issues more quickly, especially in embedded systems. 5. Maintaining documentation. Ensuring that documentation is updated as code evolves is critical, but often neglected, leading to outdated or inaccurate documentation. Integrating documentation into the development process, such as using code documentation generators, example, Doxygen, and enforcing documentation updates during code reviews, can help. Treating documentation as an integral part of the development process is essential to avoid confusion down the line. If you're enjoying the video, please consider giving it a thumbs up and subscribing to our channel. We value your input, so feel free to share your suggestions for topics you'd like to see covered in the comments section below. And that wraps up our look at the implementation phase of the software development lifecycle. Today, we covered the essentials, from how to develop code, modular code, to testing and managing versions with tools like Git. By understanding these steps and best practices, you're well on your way to building reliable, maintainable software. Thanks for watching, and we'll see you in the next video of SDLC Step. Happy learning!